Video Lecture 13B, Integrated Rate Laws. Sometimes, when studying the kinetics of a reaction, we're simply interested in how the concentration of a given reactant changes with time. We can derive such a relationship from the rate law for the reaction. Recall that rate laws show how the reaction rate depends on the concentrations of the reactants. The conversion between a rate law and an equation that shows how concentration of a reactant changes as a function of time is mathematically rigorous. However, we do want to point out that rate laws can be seen mathematically as first-order differential equations, or equations that contain derivatives. If you've taken a calculus course, or are currently taking a calculus course, you've definitely encountered derivatives. And you might also know that the opposite of taking the derivative of a given equation is to integrate an equation. This is why we call equations that show how the concentration of a reactant changes as a function of time integrated rate laws. The form of an integrated rate law, like the form of a rate law, depends on the overall order of the reaction. Therefore, we present three integrated rate laws for the most common types of reactions: first order, second order, and zero order. We start with zero order reactions. The rate law for zero order reactions shows that the reaction rate is a constant value. That is, for zero order reactions, the rate does not depend on the concentration of your reactants. The integrated rate law for a zero order reaction shows that there is a linear dependence of the concentration of our reactant there is a linear dependence on the concentration of our reactant on the time that it takes for the time that has elapsed during the chemical reaction. For a first order reaction, we've seen that the reaction rate is directly related to the concentration of reactant A. The integrated rate law shows that there is a relationship between the natural log of the concentration of reactant A and the time elapsed during the course of the chemical reaction. For second order reactions, the reaction rate depends on the square of the concentration. In the integrated rate law for a second order reaction, it is 1 over the concentration of reactant A that is dependent on the time elapsed during the course of the chemical reaction. These three integrated rate laws show the relationship between the concentration of reactant A and the time elapsed during the course of a chemical reaction for the most common types of chemical reactions. Please keep in mind that you do not have to memorize integrated rate laws. They will be given to you on exams and quizzes. One very useful application of an integrated rate law is to use these rate laws to plot kinetic data. Plotting kinetic data has two purposes. The first purpose is to determine the overall order of the reaction. The second purpose is to determine what the rate constant is. This is a very important use of integrated rate laws because it allows us to graphically determine the overall order of reactions and the rate constant for reactions, without having to go through the mathematical rigor of determining a rate law. We can show how rate laws can be used to plot kinetic data by comparing our integrated rate laws to the equation for a linear fit. The equation for a line can be represented by the equation y equals mx plus b, where m is the slope of the line and b is the y-intercept. For zero-order reactions, it is very easy to compare the integrated rate law to the equation for a line, since the concentration is linearly dependent on the time elapsed during the course of the chemical reaction. This tells us that if a reaction is zero order, plotting the concentration of reactant A versus time should give us a straight line. This line will have a slope that is equal to the negative of the rate constant, and a y-intercept that tells us the initial concentration of our reactant. To summarize this information, we've created a table. This table tells us that plotting the concentration of reactant A on the y-axis and plotting the time elapsed on the x-axis will show us that the reaction is zero order if we get a linear fit. And the slope of our best fit line will equal the negative of the rate constant. For a first order reaction, we need to do some manipulation to our integrated rate law. This manipulation gives the final result that the natural log of the concentration of reactant A is equal to minus K times T plus the natural log of the initial concentration. If we compare this to the equation of the line, we see that for a first order reaction, plotting the natural log of the concentration versus time should give us a linear plot. This plot will also have a slope of negative K. However, the y-intercept will be equal to the natural log of the initial concentration. So a reaction that is first order will give a straight line if the natural log of the concentration is plotted as a function of time. Once again, we get a slope that is negative and that is in magnitude is equal to the rate constant for the reaction. Finally, we can compare the equation for the integrated rate law for a second order reaction with the equation for a line. This shows that 1 over the concentration of our reactant is equal to K times T plus 1 over the initial concentration. If we compare this to the equation of a straight line, this tells us that plotting 1 over concentration versus time will give us a linear fit if the reaction is second order. In contrast with the other plots, the slope of this plot will be a positive value, equal to the rate constant. So in summary, if a reaction is second order, plotting 1 over the concentration versus time, will give us a linear plot where the slope is equal to the rate constant. This slide and the previous two slides show how plotting different variables on the y-axis as a function of time can allow us to determine the overall reaction order as well as the rate constant. One interesting thing we may want to know is how long it takes for half of our reactant to disappear. This time is known as the half-life for the reaction. Like the integrated rate laws, the half-life of a given reaction also depends on the reaction's order. We can use integrated rate laws to determine equations for the half-life of a reaction. Doing this gives us three distinct equations for our most common types of reactions. For a zero-order reaction, the half-life is equal to the initial concentration of reactant A divided by 2 times the rate constant. Interestingly, for a first-order reaction, the half-life is only dependent on 1 over the rate constant. That is, that the half-life does not depend on the initial concentration of our reactant. For a second-order reaction, the half-life is equal to 1 over the rate constant times the initial concentration. One important use for our half-life equations is to determine what the rate constant is for a reaction. We can apply our integrated rate laws to the following type of question. Shown on the slide is the reaction for the isomerization of cyclopropane. Cyclopropane can be converted to its isomer, propene, by heating up the reaction vessel. The isomerization of cyclopropane is first order and has a half-life of 19.3 minutes. If the initial concentration of cyclopropane is 0.0226 molar, we want to know what the concentration will be after 8.75 minutes has elapsed. For this problem, we first want to determine what the rate constant is for the reaction. We will need the rate constant when we apply the first order integrated rate law. We know that the half-life for a first order reaction is equal to the natural log of 2 divided by the rate constant. This means that the rate constant is equal to the natural log of 2 divided by the half-life. We can plug in the half-life for our isomerization reaction to obtain a rate constant of 3.59 times 10 to the minus 2 inverse minutes. Note that there's no need to convert our rate constant unit into inverse seconds, since the time given is given in minutes. Our next step is to use our given information combined with our calculated rate constant to calculate the concentration of cyclopropane when 8.75 minutes has elapsed. We can use a property of logarithms to simplify our integrated rate law. This property is that the natural log of number x divided by number y is equal to the natural log of x minus the natural log of y. Therefore, the natural log of the concentration of cyclopropane at time t divided by the initial concentration of cyclopropane is equal to the natural log of the concentration of propane after 8.75 minutes has passed minus our initial concentration. Adding the natural log of our initial concentration to both sides of our equation gives us the natural log of the concentration of cyclopropane after 8.75 minutes has elapsed is equal to our initial concentration minus K times T. We're now ready to substitute in our given information. Our initial concentration is 0.0226 molar. Our calculated rate constant is 3.59 times 10 to the minus 2 inverse minutes. And the time point that we're interested in is 8.75 minutes. This gives us that the natural log of the concentration of cyclopropane after 8.75 minutes is equal to negative 4.10393. Note that this number is unitless, as the natural log of any quantity should be. To undo the natural logarithm, we raise both sides of the equation. We raise e to both sides of the equation. This gives us the concentration of cyclopropane at 8.75 minutes is equal to e to the minus 4.10393, which equals a concentration of 0.0165 molar.